Okay, welcome all of you. So can you all hear me and see the screen? Okay, all right. So let's begin today's lectures. So tomorrow would be the end of this particular discussion session. Okay. So I plan to cover maybe linear regression today. Okay, so we already seen one algorithm for classification. So I guess all of you have a basic understanding of what we do in classification tasks. I thought that it might be instructive to discuss a different kind of an algorithm, which is linear regression in today's class. We'll learn about linear regression and we'll also see maybe again just like yesterday we'll see some parts of the code. We won't go into the details of the code. We'll just see what each part of the code does. Okay, not the details of the specific Python syntax. Okay, and yeah, so that's sort of the plan for today. Tomorrow we'll discuss deep learning. Okay, because deep learning in itself is a huge topic. So that's why I'll briefly discuss deep learning tomorrow, and probably I'll try to make you understand how to do digit recognition, handwritten digit recognition, using one of the most famous deep learning models, which is called convolutional neural networks, okay, or CNNs. And we'll end this entire workshop with tomorrow's discussion. Okay, but before I start, do you have any questions from what we covered in yesterday's session? Let me quickly go to this slide. We saw all of these things, right? Yesterday we discussed in detail that machine learning can be broadly sort of classified into three parts: supervised, unsupervised, reinforcement. We were specifically looking at supervised learning. We didn't look at any algorithm for unsupervised or reinforcement. In supervised, we saw that you can further distinguish between two different types of problems. The first one is classification problems. Okay, the second one is regression problems. So in classification problems, your output is, does anybody remember what should the output variable be in classification? What kind of variable is the output variable when we are looking at classification tasks? I used a specific term. Again, I'd like you to remember that term, okay, because it's a term which comes up quite often. Okay, so it's called a categorical variable. I hope all of you remember this term, categorical variable. Okay, but all of you must know what a category is, right? Category is like one of many different kinds of things. Okay, so a categorical variable is a variable which takes sum of finite number of values. Okay, that's what a categorical variable is. Okay, so we discussed all of these things. Then what did we discuss next? We discussed all of these applications, okay, of NLP and computer vision. Okay, we discussed the roadmap to becoming a data scientist, right? All the topics that you need to sort of cover so as to become a data scientist. Okay, and we mapped this to the syllabus that we cover at Innomatics. Okay, so today we'll look at linear regression. Okay, so but before I start linear regression, do you have any questions? If you have any questions, you can please ask them. Okay, I'll just switch to my iPad while you think about your questions. Okay. Okay, so we share my screen. So yeah, so I hope you can see my iPad screen. Can anyone quickly confirm if they can see my iPad screen? Uh, I have a question in the chat. Is it important to learn all the algorithms to be an ML engineer? Indeed, yes. I would say yes. It's important to learn all of these algorithms. And more importantly, see, if you learn all these algorithms, only then you would know when to use which algorithm. Okay. All algorithms are not sort of, equally applicable in all scenarios. Okay. So in that sense, yes, you should learn all these algorithms to become ML engineer. Okay. For example, I mean, I think told you about naive Bayes algorithm. Okay, so but you can't use naive Bayes in all situations. Okay, I mean there is an underlying assumption in the naive Bayes algorithm. Okay, the input uh, the output condition on the input should be independent. Okay, that's I mean that might not mean anything to you now. Okay, but I mean the point is that there are underlying assumptions in these algorithms. Okay, so only when you know these assumptions, okay, how do these algorithms work, only then you can make informed decisions, okay, about choosing one algorithm versus choosing some other algorithm. Okay. Okay, so now let me start with today's discussion, which would be on linear regression. Okay. So let's again first draw the diagram. Okay. Our classification that we have been seeing for I think 2-3 days now. So we saw that machine learning can be divided into three parts, right? So first is supervised, unsupervised, okay, and reinforcement learning, right? We were focusing on supervised learning, and we saw that there are two kinds of tasks in supervised learning. The first is classification, and we already saw one algorithm from this family of tasks, namely KNN, okay, K nearest neighbors. So today we are going to look at the other task, which is a regression task. Okay, and the key point to remember that in regression tasks, your output is real valued. Okay, your output is a real value. It's not one of many categories. It's a real number. Okay, and you have to predict a real number. Fine. Say for example, suppose, okay, I'm just taking an example that you might want to sort of predict somebody's height given his or her weight. Okay, that makes sense, right? So I mean, suppose I have this data set where you have somebody's weight, okay, and somebody's height. Okay, so I'm saying that this is your input and this output. So given the input, you'd like to predict the output. Okay, so suppose somebody has a weight of 65 kilograms. Okay, so everything here is in kgs and everything here is in maybe centimeters. Okay, so somebody has a weight of 65 kilograms and height of 169 centimeters. Okay, some other person has a weight of 49 kilograms and a height of 152 centimeters. Okay, now a third person has a weight of 72 kilograms and a weight of a height of 181 centimeter. Okay, and so on. Okay, so now I'm saying here, this is your X, which is the input. Okay, and this is your Y, which is the output. Fine. And you'd like to predict the output given the input. Okay, so somebody comes and tells you a weight. Now the question is, can you predict the person's height? That's the question, right? Now, the first key point to notice here is that the output Y is a real number. It's not a categorical value. It's not like predicting between cat, dog, and horse. Okay, it's a real number. It could be 169, it could be 168, it could be 168.56, and so on. It could be any real number. It's a continuous value. Okay, not one of many categories. That's the first difference. Fine. Is this making sense to all of you? Any questions on the task that we're trying to solve here? Next, we'll try to understand how to solve this task. Okay. So this is the data set. Okay. So now, suppose as before, let's draw the graph. Okay. First, let's draw the graph for this particular. I'm not going to draw the graph to scale. Okay. I'm just going to plot some numbers. Okay. So suppose one of these, so first let's define what x and y axis are. This is x axis, this is y axis. On the x axis, I want to put the weights of individuals. Okay, the weight of the individual, and on the y axis, I'm going to put the height of the individual. Fine. And now every point, okay, so if I plot a point like this, okay, it represents one person, okay, a person with with weight, say x1, okay, and height y1. Does this make sense to all of you? I'm not specifying the exact values here, okay. I'm not specifying the exact value of x1 and y1, but this could be some value. Okay, maybe this is like 50 kgs, okay, and this is like 160 centimeter, okay. I'm just calling them x1, y1. I'm not worried about what values they are. Fine. I hope this makes sense to all of you. So this is like one data point, okay, one data point like this. Okay. Similarly, I might have another data point, maybe somewhere here. Okay, this is again, suppose x2, and this is y2. Do ask questions if you're confused, okay? Because it's impossible for me to understand if you have a question or not, okay? I can't see your faces. I do not know if you're feeling confused or perplexed or something, okay? So do ask questions, okay? Suppose the third point is somewhere here. Suppose this is x3 and this is y3. Fine. And I'll plot the last point. Okay, fourth point. This is the fourth point, which is x4, and this is y4. Fine. So these are my training examples. Okay, these are the 4 training examples that I have. Right. But recall, our objective is always to go beyond the training data, to generalize, right? So in the test time, okay, or at the query time, recall at query time, I'd be given somebody's weight, right? I'd be given some, let me call it xq, query point xq, okay? And I need to predict the corresponding yq. I'm not given this. I need to predict this. Let me again pause here. Is this question clear? Because this is the fundamental question. Or do you want me to repeat? Please do not hesitate to ask me to repeat, okay? So I'm saying that you have some training points with which you have to learn, right? The relationship between x and y. Now, okay, yes, Sundar is saying repeat, yeah. So I'm saying that you have a data set, okay, where you know the x's, you know the y's, okay? These are like the examples which you use to learn, right? You practice questions, okay? You learn. At the end of practicing all the questions, you would have to take a test, right? Where somebody would come and give you the question, which in our case is the input, height, the weight, okay? But you do not know its height. You have to make the prediction, right? From the model that you learned using your training data. Right? We saw this entire process yesterday, right? You are given some training data. You learn your model using the training data. Now at query time, you'd be given some unknown input, something which you have not seen in your training data, right? Some XQ. It could be 67. Okay. Somebody gave you the number 67 for weight. Now he or she is asking you to predict the corresponding height. What should the corresponding height be? Okay. So I'm denoting this query point as XQ and the corresponding output, the height, which I need to predict as YQ. Fine. Is this making sense? Okay. Right. So now somehow, I mean, see this XQ, these are like X1, X2, X3, X4. These are your training points. You know them. You know their exact values. Okay. Something like 65, 49, 72. Maybe let me, let me construct another point here. So it's maybe 81, okay, and 190, or maybe let me reduce it a bit, 175, okay, something like this. Okay, so these are the 4 x's. Okay, this is x1, this is x2, this is x3, this is x4. Okay, these are the x1, x2, x3, x4. Okay, the corresponding y1, y2, y3, y4 are these y1, y2, y3, y4. Okay, and you're plotting these points. Okay, so these are your training points. What I've plotted on the graph are the training points, right? But now at query time, you'd be given some xq, some unknown xq. Xq can be here, xq can be here, xq can be here, it can be here, it can be anywhere, right? So given any xq, I need to make a prediction, okay, for the height, right? Right? So for given any xq, I have to predict what is the corresponding height. Okay, given any xq, I need to again predict what is the corresponding height. That is my job. That's what I need to do. Okay, and what I'll do is I'll say that I am going to fit a line. Okay, it's a choice. You might say that why are you fitting a line? I'm saying that I will fit a line. Okay, that's my choice. Okay, and therefore the name linear regression. Linear means a line. Okay, this term linear means fitting a line. So I'm going to fit a line. What do I mean by fit a line? I'll say that I'll fit a line through all of these points. Obviously, I cannot fit a line which perfectly passes through all the points. That's not possible. Clearly, these lines, these points do not fall on a line. Okay, but I'll try to find the best fitting line. Okay, we'll try to make this precise. Okay, how to find the best fitting line. But for now, just understand that I'm going to fit a line. Okay. Now let me ask you, let me draw two lines. Let me ask you, which among these two lines do you think is a better line? Is the blue line better or is the green line better through these points? The blue line is better, right? I hope everybody sees this. Does anybody feel that the green line is better? Blue, right? Everybody agrees that the blue line is better. What's happening? I mean, it's like weight and height have a linear relation. Like if weight increases, height also increases. It makes sense, right? If somebody's weight is more, his or her height should also be, larger, right? I mean, apart from some, exceptional cases. Okay, so if somebody's weight increases, height should also increase, right? That's what my data points tell me. Okay, and therefore fitting this kind of a line makes sense, right? The green line is an opposite line. It says that if your weight increases, height decreases, right? So this green line is certainly not a good choice. Okay, all right. Okay, but we will try to decide, which line to fit, which line is the best line later on. Okay, we'll have a discussion about that also, but later. Let's first now just stick with one line, which is this blue line. Okay, how I found this blue line is a different question. We'll try to answer that question later. Okay, but now suppose somebody gave me this blue line. Okay, this good blue line, which sort of passes almost through all the points, maybe. Okay, or is sort of the best fit through the points. Okay, this is the best you can do with a line. Okay, then now what do I do if somebody gives me an xq? Okay, so somebody suppose gives you some xq. Okay. Okay, so I was using superscript. So, or maybe let me stick to subscript. So somebody gave you an xq. Okay, and you need to find the corresponding yq. Okay, so now somebody gave you some xq. Okay, so suppose this is the xq. Can you tell me how do I find the corresponding yq? Can anyone give me a way of finding the corresponding yq? Let me move the xq to somewhere else. Okay, maybe here. Okay, this is where my xq is. Can you give me an easy way to find the corresponding yq? I have fitted a line. The blue line is my fit. What I'll do is I'll go up and hit the line. Okay, wherever I hit the line, I'll go and find the corresponding value of y. Okay, this is what my line tells me. Okay, and I'll go with this prediction. So my yq is going to be this. Okay, so this is my xq and the corresponding yq is this. Let me make it a bit precise. Yeah, so this is my yq. Is this making sense to all? How I'm using my line to make the prediction? That I go up and I hit the line somewhere. Okay. I see the corresponding value of y. That is going to be my prediction. If you give me xq somewhere else, okay, if you give me xq here, right, again, I'll move up. I'll hit the line somewhere, okay. I'll go and find the corresponding value of y. Maybe I need to move a little down, okay, somewhere here. So maybe this is like y3, okay. So I'll just, this is going to be my yq, okay. Let me pause here, okay, because this is the most important part. So let me pause here and you make sure that you understand this entire process. What I've done two things. First, I fitted a line. How did I fit the line? That's still a mystery. We'll try to uncover this mystery later on. Okay. But suppose somebody, by some magic, I find this blue line, right? This is the fitted line. Now I can make predictions about any XQ, right? All I need to do is you give me an XQ, which is a query point. For this weight, you want to find what is the corresponding height. What I do is I use my blue line. Okay. I go up, I hit it somewhere, I find the corresponding YQ. Okay. Again, you give me some XQ, I go up, hit the line here and find the corresponding YQ. Okay. Does anybody want me to repeat? Clear? So this in nutshell is linear regression. Okay. If you understand this, you have understood linear regression. The remaining part is just, some tedious algebra. Okay. Some mathematics. But this is the crux of linear regression, that you fit a line through all your training points. And now you use the line to make further predictions. And again, the important point is you're moving beyond your training examples. Your training examples would have only let you make predictions for x1, x2, x3, x4. You can't make predictions beyond them. But now by fitting a line, you're moving beyond your training data. Now you can make predictions about some other point also. Fine. Okay. Now, next question. Okay. So now we'll have to go into somewhat more details. Now, because we are fitting a line. Okay. Yeah. Because we are fitting a line, right? We need to write the equation of a line. Does anybody remember the equation of a line? Again, high school stuff. Chandra saying y is equals to mx plus c. Exactly. That's the equation of a line. I hope everybody remembers this. Y is equals to mx plus c. This is the equation of a line. Can anyone tell me what is m and what is c here? What is m and what is c? Slope and intercept. Exactly right. So let me write it. So equation of a line. Equation of a line is y is equals to mx plus c, where, so this m is, use another color, this is slope. Okay. And I'll tell you what slope is and what intercept is. And this c is intercept. Okay. So let's draw a line. Okay. And I'll tell you what slope and what intercept is. Suppose you have your x-axis and y-axis. Suppose this is your line. Okay. This is the line that you care about. Okay. Then m is, so first let's see what c is. Okay. C is intercept. Okay. So this value, okay, this distance is c. Wherever the line cuts the y-axis, okay, that value is called your intercept. Fine. This is your c, right? Next, you need to find what is m. Okay, m is the slope. So does anybody know the definition of slope? What is slope by definition? Again, high school stuff. Okay, I'm not teaching you any crazy maths here. Only high school mathematics. Slope of a line is nothing but tan theta. Okay, where theta is this angle. Okay, that's your slope. So this slope measures, I mean, how is the line oriented? Okay, so this particular line will have a high slope. Okay, this particular line would have a less slope. Okay, this line would have even less slope, and so on. Okay, so if you know the slope of a line and the intercept of a line, the line is fixed. Okay, the line is fixed. By fixing M and C, you fix a line. So when I say you need to sort of fit a line or learn a line, this line can be defined by its slope and its intercept. So somehow you need to find this M and this C, right? I mean, we also drew another line, the green line. That green line is also a line. That line also has a slope, also has an intercept, but a different slope and a different intercept, right? That's not a good line. Okay. We need to find the slope and intercept of the best line. That's our objective, right? So when I say to you, when I ask you that you need to find this, you need to find the best fitting line, what I mean is you need to find the best line. I mean, you need to find the slope of the best line and the intercept of the best line. Okay, because the moment you give me M and you give me C, the line is fixed. Okay, again, let me pause here. Okay, because I've told you a lot of things. Let me pause here and make sure that you have understood everything. If not, please do tell me to repeat. Okay, again, let me just repeat myself. For this line, okay, this is the intercept. Okay, this is C. Okay, and this angle, this is theta. So tan of theta is your M. Okay, you need to find this M and this C to find this best line. Okay. Okay. So I hope this is fine. Now then let's move ahead. Okay. To so as to follow the notations in machine learning, we are going to write the equation of line as not as mx plus c, but wx plus w0. Okay, this is sort of, I mean, w is the way, you know, you use, I mean, you denote your parameters in machine learning. So I'm sticking to that particular nomenclature. Okay, I won't call m and c, but I'll call w and w naught. It's the same thing. Okay, I'm just renaming the stuff. Okay, I'm just renaming the parameter. That's it. It means the same thing. W is still the slope and W naught is still the intercept. Okay. Okay. So now the next point is which line. Okay. Now comes the important question of which line. Okay. I mean, the blue line is good, the green line is bad. But how do I tell this? Okay. How do I let my computer understand this? Okay. Somehow I have to make my computer understand that the blue line is good, the green line is bad. Okay. How do I do that? Okay. That would be done through an error function. Okay. And again, this error function, loss function, you might have heard of such things, error function or loss function. It's central to any machine learning algorithm. Okay. Any machine learning algorithm, any deep learning algorithm. All of these algorithms set up a loss function or an error function. Okay. So here also we'll try to understand this very important concept in machine learning of an error function. Okay. I mean, with a very simple example. Okay. This linear regression example is the simplest one. Okay. But it lets you understand what is this loss function or what is this error function. Okay. So let's consider this blue line. Sorry. Yeah, let's consider this blue line. This blue line does not pass through all the points, right? Right. In fact, it doesn't pass through any of the points. Okay. So this blue line makes some error, right? For example, at this particular point x1, right, the blue line tells me this should be the corresponding y. Okay, this should be the corresponding y, right? But the true y is here, right? So there is an error. This is the error, right? Let me draw the error. This amount, okay, this is the error. Let me call it E1. Okay, the first error for x1. Is this making sense to all of you? What the error is? Why am I calling this the error? Because my blue line tells I should predict this, right? But my data point says no. This is the true data point, right? So there is an error. Okay, this much is the error. There is a difference between my prediction and the true value. Okay. Similarly, in this point also there is an error. Okay, this is E2. Chandu is saying, yeah, Chandu is moving ahead. Let me reach what Chandu is saying in some steps. Okay. So this is again E3. And finally, this is E4. So I have 4 errors. What would I like? Would I like my errors to be low or would I like my errors to be high? Chandu is saying low. What about others? Would I like my error to be low or high? Low, right? I would certainly like my error to be low. I don't want to make errors. I don't want to make mistakes. So I'd like my error to be low. Okay. But which error? Would I like E1 to be low or E2 to be low or E3 to be low or E4 to be low? Which one should I make low? Or should I make E1 and E2 low and not care about E3 and E4? So they're saying E1 and E4. Why E1 and E4? Because E1 and E4 are already large. Is that why you're saying E1 and E4? That's a good observation. Vikram is saying every error. So Sandhya is saying make E1 and E4 smaller. Okay. So what I can do is I'll learn a different line. Okay. So let's consider this line. Okay. Or maybe let me use a different color. So I'm running out of colors. So maybe the purple line. So consider this particular line, the purple line. In this case, you have decreased the error. Okay. So now the error is this. E1 is this, right? And E4 is this, right? Do you see this on there? But you have increased E3, right? E3 was previously this. Now you have increased E3 and you have increased E2 also, correct? So it's not like, if you should reduce E1 and E4 because these are high, but in the process of reducing them, you might increase the others. That's also again not acceptable, right? So what Vikram is saying is correct. You should try to minimize all the errors. Okay, not just one of them. Is this making sense, Saundarya? That you should try and reduce all the errors. Okay. Okay. So now our objective should be to decrease all the errors, right? So but one way of decreasing all the errors is to sort of decrease the sum of the errors. Okay. If I decrease the sum, I'll be decreasing all of them. Okay. Also, let me use a notation. Yeah, maybe let me just write something like this. Okay. So I want to minimize, okay, or decrease. Okay. When I write min, it means minimize, okay, or decrease. Decrease what? E1 plus E2 plus E3 plus E4. This is one way. Okay, I'm decreasing the sum of the errors, so I'll be decreasing all the errors. Okay, but there is a very critical problem here. Does anybody see a problem? Let me show you the diagram. Saumil is saying, sir, do we minimize sum of squares of errors also? I'm trying to reach there, Saumil. You're way ahead of me, right? I'm trying to reach there, but now I'm now asking, is there a problem with minimizing E1 plus E2 plus E3 plus E4? Saumil is saying minimize E1 squared plus E2 squared plus E3 squared plus E4 squared. Okay. Finally, we are going to do that. But first, let me ask you, is there a problem with minimizing E1 plus E2 plus E3 plus E4? Do you see any problem? And the problem should be apparent to you from the graph. Okay, you just need to look at the graph. The problem is that some of these errors are positive, some of these errors are negative, right? I mean, this error is positive, right? It's above, right? It's above the line. What is the error? So the error is like y minus y hat. Okay, this is your error. What is y? Y is the correct value, true value, which is this. What is y hat? Your model's prediction. Okay, this value. Okay, this is y. This is y hat. Y minus y hat is the error, right? So in this case, the error is positive, right? Y is above, y hat is below, right? So this number should be positive. Here it's negative, it's on the other side, right? This is y, this is y hat, right? So y minus y hat, that's negative. In this case, again, it's above the line, so it's positive. Here again, it's below the line. So it's again, this is negative. So sometimes the errors are positive, sometimes they are negative. Correct? Now, when you sum them up, some of these positives might cancel with the negatives, right? It might not cancel exactly, but I mean, if this is like +3, this is like -2, right? Some part of this is cancelled. 3 minus 2, 1 plus 1, right? You see that, I mean, if some of them are positive, some of them are negative, if you add them up, you'll reduce it, right? I mean, some of these errors would get reduced, but that's not something I want, right? If you pay careful attention, I don't care about the sign. I don't care if the error is on this side or the error is on this side. Error is error. I should not pay attention to the sign at all. Error on either side is bad. Okay, error on this side is bad. Error on the negative side is also bad. So somehow I should get rid of the sign. Okay, negative sign, right? An easy way to get rid of sign is to do square, right? Because we know if you square, the sign just gets removed, right? -2 squared is what? 4. 2 squared is also 4. Okay. Is this making sense? Why are we squaring? So Saumil said that, should we square? I'm telling you, why should you square? The reason is to get rid of the signs, because error on the positive side is bad, on the negative side is also bad. We do not care about the sign of the error, right? So if you simply sum the errors, then some of the positive errors would cancel the sum of the negative errors, which is not what we want. Okay, to get rid of the signs, we square them, right? So finally, what we would like to minimize is the sum of the squares of the errors. Fine. Any questions? Again, if you want me to repeat, we have a lot of time. Okay. I mean, I'm running a bit faster than what I expected. So if you want me to repeat, please do tell me. Okay. We have a lot of time. So if you want me to repeat, I can repeat. Okay. All right. So I guess all of you have understood, okay, what I'm trying to do here. Okay. Okay. So by the way, I can also write this thing. I mean, let me write it in a different way. I hope you know this symbol. Does anybody know what this symbol means? This is a Greek symbol. It's the capital sigma. Does anybody know what I mean if I write I is equals to 1 to 4? Summation, exactly. This is sigma and this is summation. This means summation. Okay. So if I write EI squared, this exactly means this. Okay. It's a symbol. Okay. It's like sum, take a sum from 1 to 4. Okay. Of EI squared, right? So you have to put 1, then 2, then 3, then 4. So Amil is asking, sir, can we not take modulus of errors? Very good question. Okay, that's a very, very good question, Samil. Why can't we take just E1 mod plus E2 mod plus E3 mod plus E4 mod? Okay, I'll try to answer this question maybe after some time. Okay, there's a reason why we like squares and we don't like modulus. Okay, that's a reason. I'll maybe discuss it. Okay, later on. That's a very good observation. Okay, so let's come back here. So I mean, this E1 squared plus E2 squared plus E3 squared plus E4 squared can be succinctly written like this. Okay, EI squared, sum EI squared. Okay, so you need to put first I is equals to 1, that's E1 squared, then I is equals to 2, E2 squared, then 3, E3 squared, and then 4, E4 squared. Okay, so 1 to 4. Okay, in general, right, here I just considered 4 points, right? In general, my data set will have many points. Okay, so in general, training data will have, say, n number of points. Okay, n data points. Okay, so here I consider only 4 people, 4 individuals. Okay, their heights and weights, but in general I might have some n. Okay, I do not know what n is, maybe 1,000, 10,000, something. Okay, n data points. Okay, so my error, okay, or my loss function, this is also called loss, would be summation I is equals to 1 to n and not 4. Okay, ei squared. Okay, but recall, what is ei? What is ei? Ei is nothing but yi minus y hat I, correct value minus predicted value, right? Correct value, this is y1 and this is y hat 1 minus predicted value. Okay, so I can replace the loss function with summation I is equals to 1 to n yi minus y hat I squared. This is the loss function for linear regression. Okay, any questions from this part? Okay, this is the sum of squares of errors. Okay, it's also called sum squared error. This loss function is called sum squared error. Why? Sum squared error. This is the error. True minus predicted. Let me write it. Okay, this is the true value, the correct value. Okay, this is the predicted value. Okay, true value and predicted by your line, whatever line you want. Okay, and now the final point, after which will be done. Okay, after this we'll be done with linear regression, understanding. You'd be understanding all the concepts of linear regression. Okay, once I complete this. So now recall the final point. How is y hat I calculated? Y hat I is the prediction, right? And this is where my line comes. Okay, I'm fitting a line, right? Mx plus c or wx plus w naught. So y hat I is nothing but wxi plus w naught. Okay. And now the final objective is to find this slope and this intercept, which minimizes this error, right? So you want to minimize the error. Okay, minimize this error. Summation I is equals to 1 to n yi minus y hat I. Okay, you want to minimize this. Okay, by changing what? You can change only the slope and the intercept. So I'll write them here. This is the final equation for linear regression. Okay, and we are done with linear regression. Let me summarize. Okay, let me summarize. What are we trying to do here? We are trying to fit a line through all the data points, right? Obviously, I cannot pass the line through all the data points. I'll make some errors, right? So I want to fit a line. What do I mean by fitting a line? Finding the choice of slope and intercept, which minimizes the error or minimizes the loss function. That's my objective. Okay, so you can also, this is also one possible line, but the error is very high. Obviously, the error for the green line for this point is this much is E1. Okay, this much is E2. Okay, this much is E3, this much is E4, right? So all of these values are very, very high, right? If you take the square and sum them up, it's going to be very high. So this line is certainly not the line which minimizes this particular error or this particular loss function, right? So you want to find W and W naught such that this loss is minimized. That's the best fit. That's the best choice of line through your data points. Fine. Any questions? Now we'll go and maybe see this entire process in Python. I mean, we won't discuss the code. I'll just show you what to do, how to do in Python code. Okay. We still don't know sort of how to find this W and W naught. Okay. This is still not a solution. This is like you have set up a problem. Okay. This actually is called an optimization problem, right? Recall yesterday I talked about optimization. Optimization is nothing but the study of how to minimize or maximize a function. Okay. So this is nothing but an optimization problem. You want to minimize something, okay, by changing something. You are allowed to change W and W naught. What do I mean by change W and W naught? If you change W and W naught, you're changing the line, right? Okay. So this blue line, okay, and say this line, okay, the second line that I drew, okay, they have what? I mean, how do they differ? They differ in the choice of slope and intercept. So by choosing the slope and intercept, you're drawing different lines. Okay, and these different lines would have different losses. You want to choose that line which minimizes the loss. Okay, I hope you're able to imagine this problem. What is it trying to do? Okay, what does it want to do? It wants to find the best choice of slope and intercept which minimizes the loss function. How do we do that? That's a separate question. Okay, we won't be able to address that question, not at least in this workshop. Okay, there are certain algorithms which can be used to find the best choice of W and W naught. Okay, one of them is, you might have heard of it. Has anybody heard of this algorithm? Gradient descent. Has anybody heard of this algorithm called gradient descent? Okay, I guess not. This is one of the algorithms. Chandra Singh is okay. So this is one of the algorithms which can be used to solve this particular problem. Yeah, Vikram is saying used to find minimum cost function. Exactly. Okay. So that's I mean, you have some other algorithms also, but gradient descent is the most popular algorithm to solve such optimization problems. Okay. Now coming back to I think Saumil had asked. Saumil had asked that why not use mod? Okay. The reason is, so let me draw two graphs and let me ask you. Okay. So say y is equal to x squared, okay, and y is equals to mod x. Okay, I'll plot both of these curves. So the y is equals to x squared would look something like this. Okay, and y is equals to mod x would look something like this. Okay, so this purple one is mod x, okay, and the red one is x squared. Can you tell me what's a good thing about x squared which is not there in the purple line? Again, you have to look at the graph. Let me give you a hint. Look at this part of the graph. Okay, or maybe this part of the graph. Is there something wrong with the mod x graph, which is not, I mean, the same thing is not there in the red graph, in the x squared graph, somewhere here. Stationary point. Yeah, so both of them have stationary point. Okay, Samil, both of them have a stationary point here. That's correct. Okay, both of them have stationary point. I'm saying the purple line does something which the red line does not. Do you see that this slope changes abruptly? Okay, there's an abrupt change in slope. The red curve does not change its slope abruptly, it changes it smoothly. The red curve is smooth. The purple curve is not smooth. It's pointy. It's not smooth here at 0. Okay, mathematically, smoothness has a certain name, and we have all studied. I mean, if you've taken high school mathematics, you know what I'm talking about. What is smoothness of a function? How do we capture smoothness of a function? By its derivative. Okay, by its differentiation. Okay, by its derivative. For the purple curve, the derivative does not exist at 0. Okay, it's not, it does not have a derivative here. It's non-smooth. The red curve is a smooth curve. Okay, it has a derivative throughout. That's why we prefer x squared over mod x in many situations. Okay. By the way, derivative and gradient are, I mean, similar things. Okay. Gradient is like a generalization of derivative, right? So this gradient descent can be used if you have derivatives. Okay. If you don't have derivatives, you cannot use gradient descent. Okay. So in that sense, this mod x graph is not preferable. Okay. This x squared graph is preferable because it's smooth. It has derivative everywhere. Okay. But these are like technical points. Okay. If you've understood this point, well and good. Okay. If not, I mean, just, forget it. Okay. Soundarya has a long question. So let's read the question. We calculate error for each point and it is calculated with predicted and actual value. Why it is connected with intersect and slope? So let me go back. Why is it connected with intercept and slope? That's a good question. Okay. See, how is it connected with intercept and slope? That's a very important point. Okay. See, this is the prediction, right? Sorry, this is the true value. Do you agree that this is the true value y, which is given to you? Correct. And now you're saying that this is y hat, right? And you compute the error by calculating this difference between the actual value and the predicted value, right? But now I'm asking you, how do you come up with this predicted value? How do you come up with y hat? You come up with y hat using a line. Okay. That line has an intercept and a slope, right? You can see this here, this blue line. Using this blue line, you come up with this y hat. Okay. Or maybe this y hat. Okay. Or maybe this y hat, or maybe this y hat. You come up with this y hat using this blue line, right? So this y hat has an indirect dependence on the slope and the intercept. That's how the error depends on the slope and intercept. Is this making sense, Saundarya? The prediction is made using a line and the line has an intercept and slope. That's how they are connected. Okay. Now, I mean, you might have, certain questions like, why am I fitting a line? Why can't I fit something else? Fair question. Okay. Fair enough question. But this is just a discussion on linear regression. We can move beyond linear regression also. We can do something called as polynomial regression. Okay. Which is like fitting higher dimensional things. Okay. Not just polydimensional, but some curves which are of higher degree. Okay. Those things are there. Okay. But we won't be covering them, at least for this session. Okay. Let me now quickly. So we'll stop early today. So I've discussed linear regression. We'll discuss the code briefly. I'll show you how to do linear regression and we'll stop here. Okay. For today. Vikram is saying we have to find nearest line based on least of all combinations, which can be done by creating line y is equals to mx plus c. I'm not sure if I, okay. For some reason it shows, okay, I think screen share is lost. Let me just try and reshare my screen. Yep. Yeah. I'm not sure if I understand your question completely, Vikram. So let me, so see, I think you're asking about the best line. Okay. So this, I'm just saying that this blue line is best. Okay. And say this purple line is not best. Okay. How do I say that? By computing the error. Okay. This error. Okay. This error. Okay. This blue line would have an error. This purple line would also have an error. I'm saying the blue line has the least error. Okay. Or rather choose that line, whichever has the least error, right? You can fit many lines through these points. Okay. You can fit the blue line. Okay. Or you can fit this line, or you can fit this line, or you can fit this line. I'm telling you, fit whichever line has the least error. Okay. That is your blue line. Okay. So fit that line which minimizes the error. That's why I have a minimization here. Okay. So now let me move to my laptop. Let me share my screen. And if you have any questions in the meantime, please feel free to ask them. Yep, I hope you can see my screen. Yeah, so this is simple linear regression. I'm going to work with a data set. This is the data set. I'm showing you the first five entries of the data set. It has, I think, 25 entries. Okay. It's a data set where you have the number of hours a student studies, okay, and the score that he receives. Okay, the score that he receives. I mean, you can immediately sort of think that or understand that the more you study, the better score you would receive, right? So there should be a linear dependence, right? It's like height and weight, right? If you increase weight, height should also increase. If you increase the number of hours that you study, okay, the scores obtained by you in an exam would also increase, right? So, I mean, I have a plot. Let me show you the plot. Yeah, this is the plot. Okay, this is the plot where you have the number of hours a student studies and the corresponding score. Okay, these are the training points, just like the 4 training points that I had drawn, okay, on my iPad. These are the 25 training points that you have in this data set. Okay, on the x-axis you are plotting the hours, and on the y-axis you're plotting the scores, right? And this looks like a linear relationship between the hours and scores, right? So here also I'd like to fit a line. Okay, I'd like to fit a line through this data set. Okay, that's what linear regression would do. Again, as in yesterday's session, there are some steps to build any model. Load the data. First, you have to load the data. Then you have to do data preparation, right? Where you do train, test, split, right? You divide your data set into 2 parts, the training set and the test set. You use the training set to build the model. You use the test set to evaluate your model, how good your model is. Okay. And then you train the model using linear regression. You make predictions. Okay. And then you evaluate it. These are the 5 steps. Okay. Again, this is a very, very simplistic example. Okay. I mean, real life machine learning um, code would be much more complex than this. Okay, but this sort of gives you an idea of what we do in machine learning. Okay, so this is data preparation. You're preparing the data, not so much interesting. Finally, this is where you do test and train split. We discussed this part yesterday also, right? You divide it into the training set and the test set. So here you are doing like 0.7, 0.3. So it's like 70% data goes to the training set, 30% goes to the test set. Okay. And then you fit the model. So this is the model that you import, linear regression, and you fit it. Okay. And after you fit, you evaluate your model. Okay. And your accuracy is this. Okay. This is your accuracy. So 95%, 95.6% accuracy. It's a very good model, right? 95% accuracy is very good. Out of 100 points, you'll be making mistakes only on 5 points. Okay. So I've skipped all the details of the Python code because I know that a lot of you do not yet know Python. Okay. But yeah, so this is how you would build a model. Okay. This is like one way of, this is like the simpler way of building the model. There's another pro way of building the model, which I won't discuss now. Okay. But yeah, so that's about it. Let me briefly tell you about gradient descent. Okay, I haven't told you what gradient descent does, but let me just briefly tell you the story. Okay, what gradient descent does is it starts with a random line. Okay, let me show you a diagram for gradient descent. Okay, it starts with a random line. Okay, this is not a good line. Obviously, this is not a good line, right? A good line would be a line which passes through all the data points. Okay, something like this. Okay, in the middle, right? So it starts with a random line, and then it keeps on adjusting its slope and its intercept. Okay, it changes its line. Okay, to make the error lower. Let me again say this: gradient descent is a way to find the line. Right? I already told you how do you find the line by gradient descent. Okay, we haven't discussed the gradient descent algorithm, but I'm just telling you what it does. It starts with a random line. This is the random line that it starts with. Now it adjusts or changes its slope and its intercept so as to reduce the error, right? Here, obviously, the error is very high, right? So this is not a good line. The error is high, right? So it changes its slope and intercept, okay, to reduce the error. Okay, in the next step, it has reduced the error a bit. Okay, in the next step, again, it has changed the line. Okay, so if you see carefully, the line has changed. Okay, it has not changed much. Okay, so now you have the line here. Okay, and it changes a bit. Okay, So it's adjusting. Okay, after some steps, because it's a very simple problem, after some steps it finds the best line. Okay, so it adjusts the line. Okay, and by doing this it finds the best choices line. It's still adjusting. Okay, it's still adjusting. You might not see the differences because it's very small adjustment, but the point is it keeps on adjusting and finally finds the best line through all the data points. This is what linear regression is. Okay, why root of squared errors? Yeah, okay, I mean these are like technical points. Okay, sometimes, so recall that you're squaring the errors, right? So inherently you are increasing the size of the errors, okay, by squaring it. So what you do is finally you take a root over, okay, to scale everything back. Okay, so if you take a root of square, I mean the terms would come back to the standardized form, okay, to the standard values. Okay, that's why you take a square, sorry, that's why you take a root of the final expression. Okay, I mean that's just for scaling purposes. Okay, it does not have any mathematical significance. Okay, without this root you'll have large values. Okay, with root you'll have small values, but I mean it's just proportionally different. Okay, that's about it. It's like, saying you are measuring somebody's height in centimeters, then his height is like 160, 170, right? But if you measure it in meters, it's like 1.6. Okay, so you're changing the scale. That's about it. Okay, okay. So Chandra Singh, is scaling necessary for algorithms? So it depends on what kind of scaling you're talking about. So here, I mean, when you're seeing this final square root is just for you to visualize. It doesn't play any role in the algorithm. Okay, does not play any role. This final scaling does not play any role in algorithm. You find the line, okay, then you do the square root. That's it. Okay, but some other scaling, okay, some other kind of scaling, which I think we did here. I didn't discuss that because it will take a lot of time. We do something here called normalization or standardization. Okay, so I'm calling something here standard scaler. I do some standardization. Yeah, this is feature scaling. This is a very important part. Okay, this is indeed a very, very important part of machine learning and especially deep learning algorithms. Okay, if you do not do standardization of your data, I mean it might take you a lot of time to converge to the correct solution, right? What do I mean by converge? Converge means you start with a line, you keep on finding the line. Okay, you try to find the best line. Okay, this is called convergence to the solution. Okay, the final solution is this line. Okay, this is like convergence to the solution. Here we took I don't know, maybe 10 steps. Okay, but if you do not scale your features, okay, it might take you a lot of time to converge. Okay, that's why scaling of features becomes essential, especially in deep learning algorithms. Okay, I mean, the differences are like huge, hours to like weeks. Okay, with proper scaling, you can complete your training in hours. Okay, if you do not scale it properly, it might take you weeks. Okay, so it's not like a trivial thing. Okay, it's an important part. Okay, yeah. Okay, any other questions? I hope again you have got some idea of what we do in machine learning, right? We discussed two things. Okay, we discussed classification, which is a different kind of a problem, and we discussed regression today, okay, which is again a different kind of a problem. For both of these tasks, we saw two different algorithms. For classification, we saw k nearest neighbor, right? You ask your k neighbors and take a majority vote, right? Then we saw linear regression in today's class, where we do regression by fitting a line through my data points. Okay, which line? The line which minimizes the error. Okay, all right. And how do we find that line? Using gradient descent. That's all I want you to remember from this particular session. Okay, so we are done with the content of today's class. If you need to leave, you can start leaving. I won't discuss anything concrete anymore, but if you have any questions, if you want me to repeat any part, if you want to have a chat, you can still ask your questions on the chat, or you can unmute yourself and ask questions also. See you all tomorrow at 8. Okay, so I'll see you all tomorrow at 8 and we'll discuss deep learning and we'll end this workshop tomorrow. Okay, okay, so I don't see any more questions, so then this might be a good time to stop. We'll again rejoin tomorrow at 8. Okay, and discuss deep learning. So see you all tomorrow. Bye bye.